In this video, we introduce a simple yet effective method for sparse-view Gaussian splatting. 3D Gaussian splatting represents 3D scenes using compact parametrized Gaussian primitives. When only sparse views are available, the optimization lacks sufficient supervision. This leads to inaccurate geometry and degraded rendering quality. Due to limited supervision, the Gaussians tend to overfit to the sparse input views, leading to degraded performance on unseen viewpoints. This results in artifacts when rendering from novel angles. Using a single pixel as an example, we illustrate how projected 3D Gaussians contribute to the rendered image via alpha blending. Gaussian splatting uses alpha blending to accumulate the contributions of multiple 3D Gaussians at each pixel. Here, the product term models transmittance, which attenuates the contribution of each Gaussian based on the accumulated opacity of those in front. As a result, Gaussians positioned farther along the viewpoint receive less gradient feedback due to the low visibility. Our idea is simple: we randomly drop Gaussians during training in a similar way of dropout. This is a conceptual illustration of DropGaussian. In this example, the highlighted Gaussians are the ones being dropped. The final rasterized result would appear as follows. Now, we return to the single pixel gradient example to observe how DropGaussian affects the optimization process. In this example, we intentionally dropped the front Gaussians to examine their impact on gradient propagation. As a result, the farther Gaussians received noticeably larger gradients. We present the impact of DropGaussian in this slide. The bar chart shows the number of Gaussians with large gradients, measured from the rendered scene on the right. With DropGaussian, we observe that more distant Gaussians receive larger gradients. As can be seen, the baseline 3DGS shows better reconstruction quality on the training image. However, note the region marked by the red bounding box. We rotated the camera from the training view to a novel view. In doing so, we observed a clear reduction of overfitting in the red box region. In standard Gaussian splatting, all Gaussians contribute to the pixel color through alpha blending, preserving the total accumulated value. In this example, the result pixel color is 3. However, dropping Gaussians disrupts the accumulation and lowers the total pixel value. In this example, the result pixel color becomes 2, which leads to unstable optimization. We propose opacity compensation to address the unstable optimization caused by dropping Gaussians. Specifically, we multiply the opacity of remaining Gaussians by a factor reflecting the dropped ratio, so the total pixel value remains consistent. We have observed that overfitting primarily manifests during the later stage of training rather than the initial phase under sparse-view conditions. The orange curve corresponds to the baseline 3DGS, and we observe that its test PSNR gradually decreases as training progresses, indicating overfitting in the later stages. To address this, we propose progressively increasing the dropping rate as training proceeds. Specifically, we scale the dropping rate proportionally to the current iteration over the total number of iterations. The blue curve, which represents DropGaussian, maintains stable test PSNR over time, indicating that overfitting is effectively mitigated. This is our overall architecture. We first generate initial Gaussians from sparse-view images using structure from motion. Except for the dropping process, our pipeline follows the baseline 3DGS. We optimize the Gaussians using only the photometric loss, as in the original method. Note that dropping is only applied during training. At evaluation time, all Gaussians are used without any dropping. Here, we compare our method against the baseline 3DGS on the LLFF dataset. The results demonstrate noticeable improvements in visual quality. We also compare against SOTA methods such as FSGS and CoRGS on the LLFF dataset. Despite its simplicity, our method delivers competitive results against more complex state-of-the-art approaches. On the MIP NERF 360 dataset, our method shows noticeably fewer artifacts compared to the baseline 3DGS. Compared to SOTA methods like FSGS and CoRGS, our method shows noticeably reduced overfitting. Here are additional results on various benchmark datasets. As you can see, our method produces consistent and high-quality reconstructions across diverse scenes. Thank you for watching, and please visit our website for more information.